All right, so good afternoon, everyone. This is going to be lecture number 28. But before we start, let's quickly have a recap of lecture number 27, which was on vorticity tensor, its analysis, and about finite deformations. So in the last lecture, we talked about the understanding of the vorticity tensor. That's the skew symmetric part of the velocity gradient tensor, Lij. We discussed what it means in terms of changing the or rotating the eigenvalues of d, the rate of deformation tensor, and we also analyzed it as the actual part of it as the curl of velocity, which what it does is it rotates elements at each and every point, or it rotates things around each and every point. So that's what gives it the name vorticity or spin. Next, we talked about some physical understanding of finite deformations. I talked about some special examples where we tried to understand different some special some special mappings and the corresponding understanding. So we started with simple translation, then we talked about purely rotation, then we talked about some deformations which involve stretching, some straining and rotation, and then finally we talked about a case where there was pure strain and no rotation. Okay, so I hope you've got some understanding of what these deformations mean, and you will be able to see some mappings and calculate the F tensor, which is an important tensor, giving us information about deformations and their rates. All right, so the today's lecture is going to be about some mathematics. So we'll be talking about the material derivatives of line elements, area elements, and volume elements. So you need not, uh, there is not much of a continuity between what we were doing in the last lecture and today's lecture, but this is going to be the last lecture from this chapter, and then we'll start with the next chapter, which is going to be on conservation laws. To be able to understand or develop the conservation laws, we need to understand or have these mathematical tools available to us. All right, so this is lecture number 28. We'll also talk about the transport theorem towards the second half of today's lecture, which is the beginning of the next chapter. All right, so first we'll talk about the material derivative of a line element. So what we are trying to do here is to understand if you have an element that is a line element, which is simply a vector d small x. So if we take the material derivative of that, that is the rate of change of the length or the rate of change of the vector and the line element, then how can that be written in terms of the tensors that are available to us? So you'll understand when I start writing that. So let's take a small vector d small x. So remember that d small x denotes a vector in the Eulerian or the spatial coordinate system. So in the room coordinate system, we have a small vector dx, which you could think of as the vector joining points small p and small q. So what we're interested in is the material derivative of that. That is the d by dt of this small dx. So what that means is, as time goes on, what's the time rate of change of this vector dx? It may be rotating, it may be stretching, it may be doing both. So what we can do is we can write this as d small x, as you know, is written as f d capital X. Right? So that's what we understood. D small x can be written as written in terms of the d capital X vector using the deformation gradient tensor in the symbolic notation, and this is then d by dt of f dot dx. Now, when we apply the product rule of differentiation, what we get is f with a dot on top. So a dot on top means time rate of change. That's material derivative times d capital X. And there's no second term because the time rate of change of d capital X is 0, because d capital X is defined in the reference coordinate system. So in the since the reference coordinate system is defined at a given time, that is d equal to 0. So as the configuration changes, the reference configuration still is the same. So there's no change in the reference configuration with time. That is frozen in time. So there's no meaning of d by dt of d capital X, or d by dt of d capital X actually is 0. Okay, so that is what we have here. And if you remember from the previous lectures, we wrote f dot, that is a time rate of change of the deformation gradient tensor, in terms of our velocity gradient tensor and the deformation gradient tensor. That was f dot was given as L times f, and this whole thing is dotted with dx. Okay, and again, f times d capital X can be written as d small x. So this simply becomes L times d small x. Okay, so in some cases I put a dot product between the two vectors or tensors. In some cases I don't, but they still mean. So L times d small x with or without a dot has the same meaning here. It is not an outer product, it is still an inner product. In case I forget that, just see the context and hopefully things will be clear. Okay, so this is an inner product, so this is a vector, as we can see from the left hand side. So what we get is L times d small x. So that's what we wanted. We wanted to write the material derivative of a line element in terms of the vectors and tensors that are available to us. Because in the next chapter, we'll be talking about Newton's laws of motion, the Newton's second law of motion. That's force equals mass times acceleration. So we'll have to somehow write the rate of change or the material derivatives of different quantities. So we are developing all the mathematical tools which we would need for the next discussion. All right, so the next thing we would also need is the rate of change of the length, or the square of the length. So I'll start putting a dot on the top. That means the rate of change of the material derivative. So the material derivative of dx dot dx, that's the square of the length of dx. Okay, so this can be written as twice d small x vector times d small x with the dot on top. Right, so again, applying the product rule, this is what we get. And using the same ideas, writing dx dot as L times dx, as we just derived in the line above. So we can write this as d small x dot, 2 can be taken inside, and then dx dot can be written as L dot dx. So what we have done is we have substituted d small x dot as L dot dx. Okay. Now, as you know that the L tensor, which is nothing but the velocity gradient tensor, can be written as a sum of the symmetric part, which is the d tensor, the rate of deformation tensor, and the skew symmetric part, which is the vorticity or the spin tensor. So we can write this, and this can then be expanded in two terms, where we have the first term as dx dot 2d dot dx, and the second term is dx dot 2w dot dx. And in fact, the second term, which is dx 2w dx, is a 0. Again, from the idea of double dot products. So in this case, d small x. I mean, if I write in the initial notation, this will be much more clear. So this becomes d small x I, d small x j to w I j. Okay, so that's what this term is in the initial notation, and you can see that this product of two tensors here. The first one being dxi dxj. So dxi dxj also is a tensor. It's a second order tensor. It has two free indices. And the second one, which is wij, by itself is also second order tensor. And here what we are doing is we are taking a double dot product of the two tensors. So we can see that dxi dxj is a symmetric tensor. by definition. And the second one, Wij, is a skew symmetric tensor by definition. So a double dot of a skew symmetric and a symmetric second order tensor is 0, as we have derived in our mathematical backgrounds chapter. So this term is 0. So what we get is dx dot 2d dot dx. So the material derivative of the dot product of d small x with d small x, that's a material derivative of the square of d small x length, is written as dx dot 2d dot dx. Okay. So again, remember the idea here is to write the material derivative of different quantities using the tensors that have been derived in the past. So, and you can see that somehow, I mean, in the first relation, when we said that dx dot was L times dx, so the information about the rate of change of dx, that is the d by dt, is absorbed somewhere inside L. Because L, if you remember, is a velocity gradient tensor, and velocity is the time derivative of displacement. So the rate of change, the information about how things are changing with time, is absorbed in the L tensor in the first relation. Similarly, in the second one, we also had an L, and finally we have a D. So the rate of change or time rate of change of the square of the length of d small x vector, the information of that is absorbed. I mean, the information about the rate of change is absorbed in D, because D is the rate of deformation tensor, or the rate at which the body is deforming. All right, so it's very important to understand that the d by dt, where is it gone? So that's I mean, we are deriving these things right now, and we'll be using these relations in the discussions that will be that we'll be encountering in the future. All right, so this was the material derivative of line elements, that is vectors length. Now the next one is material derivative of area. All right. So what does it mean by an area? So if we have two vectors in the reference or the undeformed configuration, so now one of these we'll call d capital X superscript 1, that's the first vector, and this is d capital X2. So if you have vectors like this, I mean, both of them are originating from point P, then the area is nothing but parallelogram. That's the area element, and we'll write that as d small s. In fact, area, as you know, is a vector. So we'll write that as d small s vector with a knot on the top. So the knot has been used to denote areas in the reference configuration. So this is what the area was in the reference configuration between two vectors, d capital X1 and d capital X2. So the area magnitude, which is the magnitude of ds naught, is simply the amount of area that is formed using the parallelogram between dx1 and dx2. You already know this from your high school mathematics. If we use the initial notation, so we can write d capital S naught, and since things are in the reference coordinate system, so we'll be using capital letters as the indices. So as you know that this can be written as epsilon ABC, and this is basically is the cross product between d capital X1 vector and d capital X2 vector. So you should write that here. So the area vector ds naught vector is written as d capital X1 cross d capital X2. So that's dx1 dx2 sine theta in terms of magnitude, and you can use your right hand screw rule or the finger rule to find the right hand thumb rule to find your direction, which for this case is out of the plane. So using initial notation, we can write this as ds naught with a capital index, and this is epsilon ABC. Sorry. So that's written using the initial notation. Sorry, I think I've made a mistake here. It should be B and C. Right. So that's the cross product written in the initial notation. All right. Now this is the reference configuration. Now we have a current configuration. So what happens is at a later time, your d capital X1 vector goes to d small x1 vector. So we'll call it as d small x1 vector, and your d capital X2 vector goes to d small x2 vector. So the area formed between the two is now different because the vectors have rotated, they have changed in lengths and so on. So the area will be written as ds without a knot. So that knot is reserved for our reference or the undeformed configuration. So there's no knot here, and of course the magnitude here is ds magnitude. That's the magnitude of the area of the parallelogram between d small x1 and d small x2. So now we can write our ds vector as the cross product between d small x1 and d small x2, which in the initial notation now can be written as dsi is epsilon ijk d small x1j and d small x2k. Okay, that's a cross product between d small x1 and d small x2 vectors. So the idea here is still the same, that what we are interested in is the rate of change of that. But before that, what we'll try to do is we'll try to write our ds I, which is the area vector in the deformed configuration, in terms of the area vector in the undeformed configuration, because they have a relation. Since we can map the transformation from the reference, since we want to map the vectors from the d capital X vectors to d small x vectors, so I mean we can use the we can use the mapping to find the d small x vector from d capital X vectors. So we can also find the areas using the same. Okay, so the area relation should also be related to the tensors that we have already defined. Okay, so let's do that. So what we'll do is we'll write this d small x vectors in terms of d capital X vectors using our f tensor. So d small x vector is nothing but the f tensors. In this case, in the initial notation, this becomes fja, and then this becomes d capital X1a. Similarly, the second dx2k becomes fkb d capital X2b. So these are the using the definition of the deformation gradient tensor. Now there's a bit of algebra here. So now what we do is we multiply both sides by fia, Sorry, we can't do that because A already exists on the right hand side. So what we'll do is we will choose our indices in a different way. We'll call this FJB and this is FKC. Okay. And this becomes B and this becomes C. So B and C are repeated indices or dummy indices. So we can choose whatever we want in this case. Okay. So A we'll reserve for the left hand side just to make the algebra a bit more convenient. Okay, so the left hand side now, what we'll do is now we'll multiply FIA, and then on the right hand side, we'll just move around the terms because it's initial notation, the order does not matter. So we have FIA, FJB, and FK. So you can see the choice of indices because then as we are used to writing A, B, C, and I, J, K in this order. So we have a nice ordering here, and then we have DX1B and DX2C written on the right hand side. Okay, so this is the whole expression that we have here written for FIA DSI. Now let's look at this expression which is underlined. Now, if you remember the definition of the determinant of a tensor or a matrix, remember, let's quickly recall that. So determinant of the F tensor was written as epsilon ijk Fi1 Fj2 Fk3. So that was the definition of the determinant written in the initial notation. There was another way to write that where you write F1i, F2j, and F3k. That's also allowed. But that's not what we want. So we also learned that in this case, the ordering is 1, 2, 3, but we can have an arbitrary order. So what we do is we multiply the left hand side by epsilon A, B, C, determinant F. So this becomes epsilon, sorry. So this, if you remember, was a part of the problem sheet that was given to you using in the beginning of the course when we were talking about the background mathematics. It's very easy. I mean, if you just want to understand this expression, you can see that if you put A equal to 1, B equal to 2, and C equal to 3, you get the determinant of F. If you end up putting any order which is anticyclic, then you get a minus determinant of F, and that is what happens when you swap any two columns of a matrix. So if you swap any two consecutive columns of a matrix, the determinant sign becomes negative. Okay, that's pretty much what it is. It's alternate column exchange written in the most general form by multiplying that by epsilon ABC. Okay, so the expression we need. So don't worry about deriving it right now. It's already been derived in the past. You can always go back to the problem sheets and see the solutions. So this is what we need. So if you can see the expression here, you have epsilon ijk, fia, fjb, fkc. So this can be replaced by epsilon abc determinant f, which is what we'll do in the next page. Right, so this is the expression we have. Now in this expression, determinant of f. Now if you remember, f was the deformation gradient tensor. So f, if you remember the definition, was x if IA was xi comma a. So and this is nothing but it tells us the rate of change. If I write this in the complete form, this is the capital X A. So there's a mapping from capital X to small x, and that's what we've been discussing throughout. So determinant of f is nothing but the Jacobian of this transformation. So the transformation from capital X to small x is denoted by the transformation matrix or the deformation gradient tensor f, and Jacobian is nothing but the determinant of f. Okay, so J Jacobian is determinant of f. We've talked about this as well in the past when talking about the inverse mappings. So finally, we can write this as epsilon ABC times the Jacobian times and it's up to me. I mean, I can write FIA as nothing but XI comma A as well. Whatever I would want to use, can use that. So XI. So what I'll do now is I will multiply both sides by capital X A comma Q. And you'll soon understand why we are doing all this. Now this term is Kronecker delta. You can see that this is nothing but del small x by del capital X A, and this is del capital X A by del small x Q. So that is nothing but it's the it's product of these two. So this is nothing but delta IQ. So delta IQ when multiplied by DSI becomes DSQ using the substitution property. So we have applied the tensor product of XIA and X capital XAQ as delta IQ. That's by definition, and this becomes DSQ. Right, and the right hand side now is epsilon ABC. Let's go back and have a look at the definition of ds naught. So we wrote, sorry, in the initial notation, we wrote ds naught as the cross product of d capital X1 and d capital X2. And if I go and see the present expression, these terms exactly give us the ds naught. So this becomes ds naught A times J, then capital X A comma Q. So all this was done to be able to write the area vector in the deformed or the current configuration in terms of the area vector in the reference or the undeformed configuration. Because that's what we have obtained. We've been able to write dsq in terms of ds not A. So that was the aim. Okay, that's an intermediate step because ultimately we want to talk about the material derivative of dsq. So the next few steps are involved just to find the material derivative of d capital SQ. But we don't simply take the material derivative. We will start with a well-known relation that is easy to prove. So it's easy to show that the material derivative of the determinant of some tensor F. Well, since F has a special meaning here, let's call it A. So if A is a matrix or a tensor, then the material derivative of the determinant of A can be written as the trace of A dot times A inverse whole multiplied by determinant of A. Okay, so A has 9 components. You find the determinant of A, and you would want to find the material derivative of that. So that can be written as the trace of the material derivative of A dotted with the inverse of A, and this whole term multiplied by the determinant of A. All right. Don't worry about this. I mean, this can be taken as a homework to show that this is indeed true. But right here, so derive this expression. But today, it's more important to be able to use this expression. Now we'll substitute F in terms of A. So what we get is the material derivative of the determinant of F can be written as the trace of F dot times F inverse times determinant of F. Okay. So that's the expression we have using a well-known relation. Now, determinant of F, as we know, is the Jacobian. So this is J dot. And then we already know that F dot can be written as L times F. That's what we have shown in the past, in the previous lectures. F dot can be written as LF. So if you have F dot dotted with an F inverse, this becomes L. Yes, this is trace of L, and then you have determinant of F is nothing but the Jacobian. So J dot is trace of L times Jacobian. Okay, so what was L? If you recall, L was nothing but the velocity gradient tensor. So Lij was Vi comma j. So by definition, L is the velocity gradient tensor. And you know that the trace of L is nothing but the sum of the diagonal components, that is L11, or in fact, it's Lii. So let's use Einstein notation here. So Lii. So this is nothing but Vi comma I. Okay, so the trace of L is written as Vi comma I. And we already know that Vi comma I denotes the divergence of the velocity vector. That is, trace of L is the divergence of velocity vector. So that can be seen from Vi comma I. So what that simplifies to is J dot, that's the material derivative of J, is written as J times the divergence of velocity. Okay, so the rate of change, the time rate of change of J depends on the value of J, or the magnitude of J, as well as the divergence of the velocity. Okay, so we are getting there. We are getting there where we will be able to write the time rate of change of the area vector. All right. So let's write the expression we just wrote for dsq. Okay. So we wrote dsq as J times well, let's use the symbolic notation. So ds vector was written as j times, let's go back and check. So let's seeing this expression, ds vector is j times ds naught vector, and capital X a comma q is nothing but f inverse. Okay, j is simply a scalar, so it can be written on the left hand side, and it's ds naught dotted with f inverse. Okay, so this is what we had just derived. Now we can multiply both sides, right multiply both sides by f. So we get ds vector dotted with an f. This becomes j times ds naught. Now we take material derivative. So the left hand side becomes ds, dot of ds times f plus ds dotted with an f dot. Okay, so that's using the product rule. So we have taken the material derivative of the whole left hand side, and on the right hand side we get j dot times ds naught plus j times ds naught dot. Now this term is 0 because ds naught was defined in the reference configuration. That was the area between d capital X1 and d capital X2. Now, since it's defined for a reference configuration, there's no meaning of, or in fact, the time rate of change of that is 0. It's this term can simply be removed. And we just derive the expression for j dot as j times divergence of v. So this becomes j times divergence of v. And this expression is then, sorry, there's no dot here. We have to be careful with using a dot because j with a dot on top is simply a scalar. Okay. And at the same time, I can, let's do it in different. This is ds dot with an f plus ds with an f dot. That's j times divergence of v ds naught. So what's important is you follow each and every step, and then we'll discuss the overall understanding of the expression that we get finally. So we post multiply both sides by f inverse. So this becomes right. Now f dot times f inverse, which is this expression, is equal to L and if I go back to the definition with expression for ds, which was this one, then ds vector is ds naught j times f inverse. Okay, so that's what we also wrote on this slide, that ds is j ds naught f inverse. So we already have that. We have j ds naught f inverse. So we can write that as ds vector. So that becomes divergence of v times ds. So now you can see that we have a ds dot that's available to us. So finally, ds dot, that's the material derivative of an area in the current configuration. That's written as divergence of velocity times the area minus ds dotted with the velocity gradient tensor L. Okay, so all this work was done to reach this expression. So that's the expression for the material derivative of the an area element. All right, so that's the second step. So first we derived the expression for the material derivative of a line element. Now we have an expression for the material derivative of an area element. Now the third and the last step is to find the material derivative of volume. Right? This one's going to be much more straightforward. So we'll be writing d omega naught as the volume in the reference configuration. So volume, to write the volume, you need three vectors. And you already know that scalar triple product between three vectors is written as the area of the parallel, is the volume of the parallelepiped. So scalar triple product. So in the reference configuration, we have three vectors, dx1 dotted with dx2 cross dx3. Okay, so these three vectors, when you write them originating from the same point, form a parallelepiped, and the area of that, the volume of the parallelepiped is written as the scalar triple product, which is nothing but also written as sometimes a box product, dx1, dx2, dx3. Again, we have talked about scalar triple product being the volume in the discussion on the mathematics in the previous discussions. So this in the initial notation is written as epsilon abc dx1a dx2b and dx3c. Right. So that's the volume of the parallelepiped that is formed between three elements, d capital X1, d capital X2, and d capital X3, which are written in the reference configuration. Now, as well, time evolves, at a current for a current configuration, the volume formed between d small x1, d small x2, and d small x3, which are the mapped versions of d capital X1, d capital X2, and d capital X3, it will be epsilon ijk dx1i d small x2j d small x3k. So that's the expression for d omega. That's the volume in the current configuration. Again, it's a very similar exercise. We can write d small xi as f ia d capital Xa Similarly, we can write d small x2j as f jb d capital X2b, and the third one becomes f kc d capital X, right? So this again we have epsilon ijk fia fjb fkc. Now the same relation that we had earlier shown. So this is epsilon abc times the Jacobian, that's the determinant of f, and then you have d capital X 1a. Now combining these expressions, what you are left with is j times d omega naught. So what we have shown is that d omega is Jacobian times d omega naught, right? So this gives us an interesting understanding here. So Jacobian, remember, is positive. Okay, so j is greater than 0, because j being less than 0 simply gives us a negative volume. Okay. Okay, so that physically does not make any sense. Now j equal to 0, we know that's also not possible, because remember that j equal to 0 means the mapping is non-invertible, which physically again does not make sense, because for every mapping you have an inverse mapping physically. Okay, there is only one and only one possible inverse mapping possible. So the inverse exists. So j equal to 0 also is not possible. Right? What does j equal to 1 mean? That d omega is equal to d omega naught. Okay, so for any time, if you have j equal to 1, that means the volume at that time is equal to d omega naught. Now, if j is equal to 1 for all times, that is any time you take, j is always equal to 1, that means the motion is isoperic. So j, I put 3 equal to here, so that basically means it's identically equal to 1 always. So this implies isocoric motion. Isoporic means same volume. So if j is always equal to 1, that means all the volumes at all times will be equal to d omega naught. That means the volumes are not changing. That means it's isocoric, same volume. Right? I mean, finally, remember the aim here is to find the material derivative of d omega. So we start with d omega with a dot on top. That's material derivative, which we know we just wrote d omega as j times d omega naught. So let's take the material derivative of that. So this becomes j with a dot on top times d omega naught. And there is no time rate of change of d omega naught, because d omega naught is defined in the reference configuration. So d omega naught with a dot on top is equal to 0. Right. Just a second, I need to put my laptop on a charger. Should work now. All right. So this j dot, as we already know, can be written as j times the divergence of velocity. We have shown that in the past, and then we have a d omega naught. Now, what is j times d omega naught? That is nothing but d omega. Okay, so finally, what we have is the material derivative of d omega, that is d omega with the dot on top, is the divergence of velocity times that volume d omega. So what does that tell us? So if d omega dot is always 0, that is for all times if the rate of change of the volume is 0. That's the same as saying the volume remains constant. Okay, so if the volume remains constant always, that means d omega with the dot on top is always 0. So if that is the case, the only way that can happen is the divergence of velocity is 0. Okay, because d omega cannot be 0. D omega is a finite volume. What we are saying is the rate of change of that is 0, so that remains same. So on the right hand side, the only way that is possible is divergence of velocity is 0. Okay, so what that means is for isochoric motion, the divergence of velocity is 0. Okay, so that's another expression that we have found out for isochoric motion. And the other one we found out was that Jacobian is 1. All right. We will understand more about the divergence of velocity being 0 in the future. But for now, whatever we have derived mathematically is enough for our understanding. So isochoric motion means when the volume does not change with time, and that simply means the divergence of velocity has to be 0. So the velocity field will have certain properties that it will be solenoidal, that is, its divergence will be 0. All right, so that brings us to the end of this chapter. Now we don't have enough time to start with the next chapter, so we will not discuss about transport theorem today. So let me remove that. So before we close this discussion, I would just want to iterate that the tensor F. So there were two main tensors in this chapter. We had the F tensor and we had the L tensor. So the F tensor is the deformation gradient tensor. It governs the stretch of line elements, area and volume changes. So it tells us about the changes in line, area and volume elements. Why do I say that? Well, if we look at this volume expression, then this one, so d omega was written as j times d omega naught, and j is nothing but the determinant of f. So f tells us how the volume changes from the reference to the current configuration. Going back a bit, let's see what we derived for ds. This expression. So ds, which was the area in the current configuration, was written in terms of j, which is determinant of f, and f inverse. So again, it is f that has the information about the area change as we go from the reference to the current configuration. Okay. And similarly, the case is for the line elements by definition of dx being equal to f times d capital X. So what we see is that the F tensor contains information about the change in line area and volume elements as we go from the reference to the current configuration. Okay, and the L tensor gives us information about the rate of this change. Okay. Again, looking at this expression, the rate of change of omega is the divergence of velocity. Divergence of velocity was nothing but the trace of L. Okay, so it's the L tensor that is contained here to give us the information about the rate of change of omega, d omega. Similarly, for the rate of change of area, which was this expression, we had divergence of velocity, which was nothing but the trace of L, and then we had the L here again. And again, going back to the rate of change of dx, vector, that's dx with a dot on top, is got an L here, the expression. So you can see that L contains the information about the rate of change, the time rate of change of the line, area, and volume elements in the as we go from one configuration to the other. So that brings us to the end of this chapter, and I'll be happy to take any questions if you have. So if there's no question, then I'll see you next Friday. Thank you.